You think Ice Age hunters faced down mammoths with strength and courage, hurling spears at a charging giant? Forget that picture. Science has just revised it. The real weapon did not work like a thrown spear at all. It worked like an engineering trap, a pike anchored into the ground, which the animal met on its own, at the full speed of its own charge. This is not a story about muscle. It is a story about how a small, physically vulnerable group of people calculated the physics of a 9-ton animal so precisely that its own weight and speed worked against it. Before we go any further, please subscribe to this channel. Your support genuinely helps us keep making films like this one. Thank you. Now, let's talk about a weapon that has been misunderstood for the better part of a century. Picture the Ice Age landscape of North America roughly 13,000 years ago. Herds of woolly mammoths moved across the open grassland, animals standing up to 4 meters at the shoulder, weighing as much as 9 tons, heavier than 2 adult African elephants combined. Alongside them, mastodons, shorter and stockier, but no less formidable, giant ground sloths taller than a modern giraffe when reared onto their hind legs, and short-faced bears capable of standing nearly 4 meters tall. Into this landscape walked a comparatively fragile newcomer, Homo sapiens, standing perhaps 1.70 meters, weighing perhaps 80 kilograms, carrying nothing but stone, wood, sinew, and an unusually large brain. It is worth pausing on exactly how strange and how genuinely dangerous this Ice Age landscape actually was. Because the mammoth, however impressive, was only one member of an entire community of outsized animals that modern viewers have no direct point of comparison for. Giant ground sloths, several distinct species ranging across the Americas, present a particularly striking example. The largest, Megatherium, reached roughly 6 meters in length when fully stretched out and could rear onto its hind legs to a height exceeding 4 meters, taller than a modern giraffe's head. Despite a diet consisting primarily of vegetation, these animals were built with enormous curved claws, some exceeding 20 centimeters in length, originally evolved for stripping vegetation and digging, but fully capable of inflicting serious injury on anything that pressed too close. Fossil trackway evidence recovered from New Mexico even preserves what researchers interpret as a documented encounter between early humans and a ground sloth, human footprints overlapping and interspersed with sloth tracks, in a pattern suggesting a tense, circling standoff rather than a straightforward approach. Short-faced bears, the largest terrestrial carnivorans known to have existed in North America during this period, stood nearly 4 meters tall when reared onto their hind legs, with proportionally longer limbs than modern bears, suggesting they may have been capable of sustained pursuit at speeds a human sprinter could not hope to outrun. Alongside them roamed dire wolves, heavier and more powerfully built than modern grey wolves, hunting in coordinated packs across the same open landscapes. Early human groups were attempting to navigate. Saber-toothed cats, their iconic elongated canines capable of delivering devastating puncture wounds to the throat or abdomen of prey, many times their own body weight, represented yet another apex predator, sharing this same crowded ecological stage. Beyond the predators, herbivorous megafauna diversity in Ice Age North America considerably exceeded anything visible on the continent today. Native horses, genetically distinct from the domesticated horses later reintroduced by European colonization, grazed alongside camels, an animal family that, remarkably, originated in North America before later populations migrated across the Bering Land Bridge into Asia and across the emerging Isthmus of Panama into South America. Giant bison, carrying horn spans considerably wider than any modern bison, and glyptodonts, armored mammals related to modern armadillos but reaching the approximate size and weight of a small car, their backs covered in a solid dome-shaped bony carapace, rounded out a herbivore community of a scale and diversity that has no modern equivalent anywhere outside sub-Saharan Africa. Into this landscape, crowded with animals capable of killing a human being through simple size, speed, or specialized weaponry, walked a species carrying none of these advantages natively. No claws capable of piercing thick hide. No running speed capable of outpacing a genuine predator across open ground. No natural armor, no venom, no size advantage of any kind. What Homo sapiens carried instead was almost entirely cognitive and social. The capacity for detailed forward planning, the ability to communicate complex, specific strategic information between individuals, and, critically for the story this film is telling, the capacity to design, test, and progressively refine physical tools capable of substituting for every one of the natural advantages evolution had denied our species outright. The physical mismatch here is worth sitting with, because it is the central puzzle this entire film is built around. A single mammoth outweighed a single human hunter by a factor of well over 100 to 1. A mammoth's trunk alone could deliver enough force to break bone. Its tusks, in a defensive or aggressive charge, could impale with ease. And yet, the archaeological record is unambiguous. Humans across North America and across much of the rest of the inhabited world during the same broad period regularly engaged, processed, and depended upon these animals for food, for hides, for bone and ivory tools, for fuel in landscapes often short on wood. The question of exactly how they managed this, what specific technology, what specific technique allowed a creature so small to consistently prevail against a creature so large, has occupied archaeologists for the better part of a century, and the answer widely accepted for most of that century turns out, according to research published in 2024, to have been substantially wrong. The technology at the center of this story is known to archaeologists as the Clovis point, a distinctively shaped fluted stone blade typically napped from chert, flint, or jasper, ranging in size from roughly the width of a human thumb to the length of a smartphone. More than 10,000 Clovis points have been recovered across North America since the type was first formally identified near Clovis, New Mexico in the 1930s, making it one of the most abundant and most thoroughly studied stone tool traditions anywhere on the continent. Radiocarbon dating places the Clovis tradition at roughly 13,050 to 12,750 years before present, a remarkably narrow window for a technology found scattered across an entire continent, suggesting either extraordinarily rapid spread or a shared technological tradition maintained with unusual consistency across a wide and mobile population. For most of the 20th century, The dominant assumption about how these points were actually used was straightforward, intuitive, and rarely questioned with the rigor it perhaps deserved. Clovis points, mounted on wooden or bone shafts, were assumed to have functioned as thrown spears, weapons hurled by a hunter, sometimes with the assistance of a separate throwing tool called an atlatl, a device that extends the effective length of a thrower's arm and can significantly increase the velocity of a projectile. This is the image that has saturated popular culture for generations. A hunter drawing back, aiming, and releasing a spear toward a charging or fleeing animal. The sharpened stone tip finding its mark through raw athletic skill and practiced aim. It appears in museum dioramas, in documentary reenactments, in video games, in feature films depicting prehistoric life. It is, by any measure, the default mental image most people carry when they picture Ice Age hunting. The atlatl itself deserves closer examination, both because it represents a genuinely elegant piece of prehistoric engineering in its own right, and because understanding its actual mechanical function helps clarify exactly what the 2024 Berkeley findings are and are not. Revising. An atlatl is, in its simplest physical description, a rigid shaft, typically 50 to 60 centimeters in length, fitted with a hook or spur at one end that engages a corresponding notch in the base of a separate, lighter dart or spear. The thrower grips the atlatl itself, not the dart directly, and the mechanical principle at work is one of extended leverage. By effectively lengthening the thrower's arm, the atlatl allows the hand to travel through a longer arc during the throwing motion, imparting substantially greater velocity to the dart than an unassisted throw could achieve. Experimental archaeology conducted with faithful atlatl reconstructions has recorded dart velocities exceeding 30 meters per second in skilled hands, comparable in some measurements to velocities achievable with early archery equipment, and considerably beyond what an unaided human throwing arm can generate with a comparable projectile. This raises an obvious question the Berkeley findings help resolve. If atlatl thrown darts were capable of genuinely high velocities, why would Byram and Sunseri's comparative and experimental evidence point toward a braced, ground-planted system instead? At least for engaging the very largest and most dangerous animals in this landscape. The answer appears to lie in the specific physics of the problem at hand. Even a dart thrown at considerable velocity by a skilled atlatl user carries a fraction of the kinetic energy present in several tons of charging mammoth. Byram and Sunseri's central insight was that, against an animal of this particular scale, a thrown weapon, however fast, still depends entirely on the thrower's own generated force to achieve meaningful penetration, whereas a braced weapon converts the animal's own vastly greater mass and velocity directly into penetrating force. A fundamentally different and, for this specific category of prey, considerably more effective physical strategy. It is worth returning briefly to the atlatl technology discussed earlier, because a specific class of archaeological artifact associated with it, small, carefully shaped and often decorated stone objects known as banner stones, along with their bone and antler equivalents called atlatl weights, offers an additional window into just how refined this broader Ice Age toolkit had already become well before the Clovis-specific braced pike innovation this film has centered on. These weighted objects, typically mounted at a fixed point along the atlatl shaft itself, functioned as a counterbalance, subtly shifting the implement's center of mass in a way experimental archaeology has demonstrated can measurably increase both throwing accuracy and the smoothness of the release motion, though researchers continue to debate the precise magnitude of the resulting performance improvement. Their presence across a wide range of North American sites, often crafted with a level of symmetry and finish considerably exceeding what pure function alone would strictly require, suggests a hunting toolkit already subject to careful, iterative refinement well beyond the minimum viable design, further supporting the broader picture this film has developed of Ice Age hunting technology as an actively developing engineering tradition, continuously improved and refined across many generations, rather than a single static toolkit arrived at once and left unchanged. This does not mean the atlatl was irrelevant to Ice Age hunting broadly. The archaeological and ethnographic record strongly suggests atlatl-thrown darts remained the primary technology for engaging smaller and mid-sized game throughout this period, and for thousands of years afterward, across societies worldwide, precisely because thrown weapons offer genuine advantages. The braced pike approach cannot match. The ability to engage prey from a distance without requiring the animal to actually charge into a fixed position, and the flexibility to pursue smaller, faster animals across open terrain, where planting a static weapon in advance simply is not a viable option. The braced pike hypothesis, Byram and Sunseri advanced, applies specifically and narrowly to the particular tactical problem of engaging the very largest, most dangerous megafauna, the animals whose sheer mass made a thrown weapon's limited kinetic energy insufficient on its own, and whose charging behavior, when successfully provoked or encountered, could be turned into the solution to that exact problem. This distinction matters for understanding the full toolkit available to Ice Age hunters. Rather than a single universal weapon technology applied indiscriminately to every animal in this crowded landscape, the emerging picture is one of a genuinely differentiated technological repertoire. Atlatl thrown darts for the majority of encounters, reserved specifically for animals within a size and danger range where thrown kinetic energy alone could reliably suffice, and an entirely separate, purpose-engineered braced system reserved for the comparatively rare, high-stakes encounters with animals whose mass made every other available option considerably less viable. The problem, as a research team at the University of California, Berkeley would eventually demonstrate, is that this default image had never actually been tested against the physical realities of what throwing a stone-tipped spear at an animal weighing several tons would actually require, and what such an impact would actually do to the weapon itself. Before we reach that 2024 turning point, it is worth understanding how genuinely unsettled this question already was within the archaeological community in the years immediately preceding it, because the popular thrown spear image was, by the early 2020s, already under serious internal challenge from researchers examining the physical evidence far more closely than earlier generations had. A study published in the Journal of Archaeological Science in 2021 approached the question through microscopic wear analysis, examining the specific pattern of chips, fractures, and edge damage preserved on the surviving points themselves, and comparing that pattern against the kind of damage produced experimentally when stone tools are used in different ways. The researchers behind this study reached a genuinely startling conclusion. The breakage patterns preserved on many Clovis points did not resemble the damage one would expect from repeated forceful impact against large animal bone and tissue of the kind a weapon plunged or thrown into a mammoth's body would be expected to sustain. Instead, the wear patterns more closely resembled those produced by cutting and slicing motions, the kind of damage associated with a handheld knife used for processing meat and hide after an animal had already been acquired, rather than damage associated with the weapon's use as the actual instrument bringing the animal down in the first place. This raised a genuinely destabilizing possibility. What if Clovis points were never primarily hunting weapons at all, but butchering tools, used to process animals that had died from other causes, or been driven into vulnerable positions by other means entirely? This was not a small or easily dismissed claim. It directly challenged the near-universal assumption, embedded in decades of prior scholarship, that Clovis points represented direct evidence of an active human hunting technology capable of engaging the largest animals on the continent. The response arrived the following year. A separate study published in the same journal in 2022 approached the same underlying question from a different angle entirely. Not microscopic wear on the points themselves, but the wound evidence preserved directly in mammoth and mastodon skeletal remains recovered from documented kill and processing sites across North America. This research identified deep, penetrating wound channels in several skeletal specimens, wounds whose depth, angle, and characteristic shape were difficult to explain through any mechanism other than a sharpened stone point being driven with considerable force into the animal's body during its life or at the moment of its final incapacitation. This evidence pointed in the opposite direction from the 2021 knife use study. It suggested Clovis points genuinely were functioning as an active hunting technology capable of penetrating deep into an animal's body in a manner fully consistent with their use as the tip of some kind of weapon system. By 2023, the field found itself holding two seemingly incompatible bodies of evidence. Microscopic wear analysis pointing toward butchering, skeletal wound evidence pointing toward active weaponry. Both lines of evidence were methodologically sound. Neither could simply be dismissed. And archaeologists, working with an incomplete physical record, the stone points themselves survive across 10 millennia. But the wooden shafts, the bindings, the adhesives, and the other organic components of the complete weapon system almost never do, lacked a clear way to reconcile the two. It was against this specific backdrop of genuine, unresolved scientific tension that the Berkeley team, led by research associate Scott Byram, working alongside anthropologist Jun Sunseri, approached the question in 2024 with a fundamentally different method. Rather than examining the stone points in isolation, they set out to reconstruct and physically test the complete weapon system as an integrated whole, drawing on an unusually wide body of comparative evidence. that earlier researchers, working within narrower disciplinary silos, had largely overlooked. Byram and Sunseri began not in the laboratory, but in the historical and ethnographic record, conducting a systematic review of documented accounts spanning multiple continents and multiple centuries of how human hunters and warriors have used pole weapons against large, dangerous animals throughout recorded history. What they found was a consistent, cross-cultural pattern largely absent from prior Clovis research. Accounts of hunters confronting large predators or dangerous game not by throwing a spear, but by planting the base of the weapon firmly against the ground, angling the point upward and outward toward the approaching animal, and allowing the animal's own forward momentum to drive the point deep into its body as it closed the distance. This technique appeared in historical accounts of hunters confronting bears in Russia, of hunters engaging lions in parts of southern Africa, and notably in the broader military history of pike infantry formations specifically developed across multiple historical periods and continents to counter cavalry charges. Infantry who understood that a stationary, ground-braced point, met by a charging horse's own momentum, could deliver a far more effective result than any weapon a foot soldier could realistically throw or thrust with arm strength alone against an animal moving at speed. This comparative pattern gave Byram and Sunseri a specific, testable hypothesis that Clovis points were never designed primarily as thrown projectiles at all, but as the business end of a braced pike system, a weapon planted into the earth and angled to receive a charging animal, engineered to convert the animal's own mass and velocity into the force required to drive the point deep into vulnerable tissue, without requiring the hunter to generate that force through their own throwing or thrusting strength. It is worth spending more time with the specific ethnographic and historical evidence Byram and Sunseri assembled, because the sheer geographic and temporal breadth of their comparative dataset is a significant part of what makes their conclusion so persuasive. And it illustrates a broader methodological point about how effective archaeological reasoning often works. Not through a single decisive discovery, but through the patient accumulation of comparative pattern across sources that, individually, might each seem circumstantial. Their review documented accounts of Siberian and Russian hunters confronting brown bears using precisely this braced pole technique well into the modern historical period, the hunter kneeling behind the planted weapon and using the bear's own charging aggression as the mechanism of engagement, rather than attempting to overpower the animal through a direct thrown or thrust attack that a bear's own considerable strength and thick hide could often absorb or deflect. Parallel accounts from various hunting traditions in southern Africa describe broadly comparable techniques used historically against lions, an animal whose combination of speed, power, and aggression makes any direct thrown weapon approach considerably riskier than a prepared, braced position allows for. Perhaps the most illuminating comparative evidence, however, comes not from hunting traditions at all, but from military history. Pike infantry, formations of soldiers wielding long, ground-braced or forward-angled poles tipped with metal points, developed independently across numerous historical periods and numerous unconnected cultures specifically as a countermeasure against cavalry charges. Swiss pike squares in medieval and early modern Europe, Macedonian sarissa armed phalanxes in antiquity, and comparable formations documented in East Asian military history across multiple dynasties. In every one of these independently developed traditions, the underlying tactical logic is identical. A mounted attacker's own momentum, when it meets a sufficiently braced and angled point, becomes the primary source of the resulting force, far exceeding what an individual foot soldier could achieve by attempting to thrust a weapon into a moving horse and rider through arm strength alone. Byram has explicitly drawn this parallel in describing the Clovis findings, noting that the underlying physics, a smaller, more vulnerable party using a larger attacker's own charging force against it through careful angling and ground bracing, recurs across human history whenever a comparatively weak defender needed a reliable method for engaging a much larger, faster-moving threat. The construction of the actual experimental rig used to test this hypothesis against Clovis-specific materials involved considerable attention to historical accuracy. Replica points were knapped using traditional percussion and pressure flaking techniques, matching the tool marks visible on genuine archaeological specimens. Hafting followed the specific fluted base pattern unique to Clovis technology, using sinew binding and heated pine pitch as an adhesive. Both materials confirmed through residue analysis on genuine artifacts recovered from documented sites. The wooden shaft itself was selected and shaped to match the diameter and material properties inferred from the rare, preserved organic shaft fragments that have survived at a small number of exceptionally well-preserved archaeological sites, supplemented by a bone foreshaft component, a shorter, harder secondary shaft segment inserted between the stone point and the main wooden shaft. A design feature documented at several Clovis-era sites, and one the research team specifically incorporated into their reconstruction, after recognizing its likely functional role in the weapon's overall performance under impact. Testing this hypothesis required building a physical rig capable of measuring exactly what happens when a braced, stone-tipped shaft receives a heavy, fast-moving impact. The Berkeley team constructed a testing platform in which a weighted object could be dropped from a controlled height onto a replica Clovis point, mounted according to the fluted hafting pattern preserved on genuine archaeological specimens, lashed with sinew and pine pitch to a wooden shaft, reinforced with a bone foreshaft in the manner the original artifacts strongly suggest. In one documented test sequence, an 11.34 kilogram weight was released from a height of 35 centimeters directly onto the braced weapon system, with high-speed photography capturing the impact sequence in fine temporal detail. What that high-speed footage revealed was genuinely striking, and it directly explains a structural feature of Clovis points that had puzzled researchers for decades. The distinctive fluted channel running up from the base of each point, long assumed to serve primarily as a hafting aid for attaching the stone to its shaft. The footage showed that upon impact, the stone point did not simply hold rigid and punch straight through tissue like a fixed blade. Instead, the point began to recede backward into the specially designed shaft system, as the impact force increased, with the shaft itself progressively splintering and expanding outward in a controlled, engineered fashion around the retreating stone tip. Byram and his colleagues describe the resulting wound mechanism as functioning much like a modern hollow-point bullet. Rather than creating a single narrow puncture, the expanding, splintering weapons system was capable of producing significantly more extensive internal damage than a simple fixed point of the same size ever could, converting the tremendous kinetic energy of a multi-ton animal's own charge into a wound profile far more consequential than anything a human arm, throwing or thrusting alone, could plausibly generate. This finding elegantly resolves the apparent contradiction between the 2021 and 2022 studies that had left the field genuinely divided just 2 years earlier. If Clovis points functioned primarily as the tip of a ground-braced pike system, engaging animals through the animal's own charging momentum rather than through a human throwing or thrusting motion, the specific breakage and wear patterns identified in the 2021 microscopic study become considerably easier to explain. Points used this way would indeed show damage patterns distinct from a simple thrown or hand-thrust weapon, since the entire mechanical loading process, impact, recession into the shaft, controlled splintering, is fundamentally different from either alternative. And the deep, penetrating wound channels identified in mammoth and mastodon remains by the 2022 study become fully consistent with this mechanism as well, since a braced pike system receiving the full charging force of a multi-ton animal would be expected to produce precisely this kind of deep, forceful penetration, considerably deeper and more forceful, in fact, than most human-generated throwing or thrusting force could achieve unassisted. As Byram put it in describing the broader significance of the finding, this ancient design represented a genuinely sophisticated innovation in hunting strategy, one offering a rare, tangible window into survival techniques that were very likely employed across much of the inhabited world for millennia, not merely within the specific North American context most closely associated with Clovis technology itself. The core insight, using an animal's own charging force against it, rather than attempting to overpower that force directly, appears based on the comparative historical and ethnographic evidence Byram and Sonseri assembled, to represent a genuinely widespread solution to a genuinely universal problem. How does a physically overmatched hunter safely and effectively engage an animal capable of inflicting fatal injury through sheer size and momentum alone? It is worth pausing here to note that the Berkeley researchers themselves were notably careful in their published work and in subsequent public statements not to overstate the certainty of their conclusions. Sonseri specifically cautioned that conclusions in this kind of experimental archaeology should never outrun what the experiments themselves and the broader archaeological record can actually support. Their initial testing platform, while genuinely revealing about how the weapon system behaves under controlled impact, involved a static wooden plank standing in for animal tissue, rather than a true biological analog. The team has indicated plans for further testing involving a more anatomically realistic mammoth-scale target constructed from ballistics gel mounted on a moving mass, work that would allow considerably more precise modeling of exactly how this weapon system would have performed against genuine animal tissue and bone under realistic charging conditions. Science of this kind advances incrementally, and the planted pike hypothesis, however well supported by the 2024 findings, remains a hypothesis still undergoing active refinement rather than a fully closed question. While the Berkeley team's 2024 findings addressed the mechanical question of how Clovis-era weapons likely functioned, a separate and remarkable piece of physical evidence reported the previous year addresses an equally important question. Just how far back in time this general category of technology, sharpened points capable of engaging the largest animals on the continent, actually extends. In 2023, in the journal Science Advances, a research team led by Michael Waters at Texas A&M University published a detailed reanalysis of material recovered decades earlier from the Manis site in Washington state, where a partial mastodon skeleton had been excavated in the 1970s. Using modern computed tomography scanning technology unavailable to the site's original excavators, the research team digitally reconstructed a broken bone fragment embedded directly within one of the mastodon's ribs, virtually reassembling the fragment with a matching piece recovered separately from within the animal's skeletal remains. The reconstructed object proved to be a deliberately shaped, sharpened projectile point, crafted not from stone but from mastodon bone itself, bearing the characteristic thin, broad, smoothly worked cross-section of a genuine human-made weapon tip, rather than any naturally occurring bone fragment or breakage pattern. Radiocarbon dating placed this specimen at approximately 13,900 years before present, several centuries earlier than the classic Clovis tradition, situating it firmly within a period researchers call the Böhling-Alleröd, a relatively mild climatic interval within the broader span of the terminal Pleistocene. This makes the Manis point, at the time of its publication, the earliest direct physical evidence of humans actively engaging megafauna anywhere in North America, south of the great ice sheets that then covered much of the continent's northern reaches. A bone weapon tip embedded directly in the rib of the very animal it had struck, preserved by pure chance for nearly 14,000 years, until modern scanning technology finally revealed exactly what earlier excavators had been unable to fully identify using the tools available in the 1970s. The original 1970s excavation at the Manis site and the decades-long path that eventually led to the 2023 reanalysis is itself a genuinely instructive story about how archaeological evidence can sit within the scientific record for a very long time before the right technology finally arrives to properly interpret it. The site was first excavated by archaeologist Carl Gustafsson, beginning in 1977, after a farmer clearing land near Sequim, Washington, uncovered mastodon bones while operating heavy machinery. Gustafsson's excavation recovered a substantial partial mastodon skeleton, and he noted at the time what appeared to be a bone fragment embedded within one of the animal's ribs, proposing even then that it might represent evidence of a human-made weapon predating the classic Clovis tradition. This was, at the time, a genuinely bold and somewhat premature claim, made using only visual inspection and conventional X-ray imaging. Technologies that could confirm the fragment's presence within the bone, but could not conclusively demonstrate that it was a deliberately shaped human artifact, rather than a naturally occurring bone splinter or an artifact of the fossilization process itself. The claim consequently received a skeptical reception from much of the archaeological community throughout the following decades, filed away as an intriguing but ultimately unproven possibility, rather than an accepted piece of evidence. The situation changed decisively only when Michael Waters and his research team at Texas A&M University revisited the original specimens using computed tomography scanning technology, a medical and industrial imaging technique capable of generating detailed three-dimensional reconstructions of a solid object's internal structure without requiring any physical destruction of the sample itself. This technology allowed the research team to do something Gustafson's original 1970s equipment simply could not: digitally separate the embedded bone fragment from the surrounding rib tissue with genuine precision, and then computationally reunite that fragment with a second, previously separate bone fragment recovered from elsewhere within the original excavation. A piece the original team had catalogued but had not definitively connected to the embedded fragment. When digitally rejoined, the two pieces formed a single coherent object, whose thin, broad, deliberately shaped cross-section left little reasonable room for interpretation as anything other than a genuine human-manufactured projectile point. Radiocarbon dating conducted as part of this same reanalysis, using techniques considerably more precise than what had been available at the time of the original 1977 excavation, placed the specimen firmly within the Bolling-Allerød interval, confirming Gustafson's original, long-doubted proposal roughly 46 years after he first advanced it. Gustafson did not live to see this vindication. The confirming study was published after his death, a genuinely bittersweet resolution to a claim that had waited nearly half a century for the specific technology required to settle the question definitively. The Manis case stands as a valuable reminder that archaeological evidence, once carefully excavated and properly catalogued, does not expire. It simply waits, sometimes across an entire scientific career, for analytical tools precise enough to finally extract everything the evidence actually contains. The significance of the Manis discovery extends beyond simply pushing the timeline earlier. It demonstrates that the broader technological tradition of engineered, hafted projectile points designed specifically to engage massive animals predates the classic stone Clovis tradition by several centuries, and that this tradition was flexible enough in its raw materials to incorporate bone as readily as stone, depending on what resources a particular group had available. It also stands as a rare instance in the archaeological record where the connection between weapon and animal is beyond reasonable dispute. Not an inference drawn from wear patterns or comparative testing, however carefully conducted, but a physical point still lodged, after nearly 14 millennia, exactly where it originally came to rest. Understanding the weapon technology itself, however sophisticated, only addresses part of the underlying puzzle this film opened with. A single braced point, however cleverly engineered, still required an enormous amount of coordinated human behavior surrounding it in order to function as an effective and repeatable hunting strategy against an animal as large, as intelligent, and as potentially dangerous as a mammoth. Ethnographic and archaeological evidence drawn from hunting societies documented across multiple continents and multiple historical periods consistently points toward cooperative, landscape-based strategies as the essential complement to any individual weapon technology when the prey involved is this large. Rather than a lone hunter confronting a mammoth in open country, the more probable pattern, supported by the physical arrangement of documented kill and processing sites, involved coordinated groups working together to identify vulnerable individual animals. The young, the old, the injured, or those temporarily isolated from the protective structure of a larger herd. And to use terrain itself as a tool, guiding a targeted animal toward natural features such as bogs, narrow ravines, or riverbanks where its mobility became significantly restricted, and where a braced pike system positioned in advance at a chosen choke point could be deployed with maximum tactical advantage rather than relying on chance encounter in open, unrestricted terrain. Fire, too, appears to have played a documented role in several regional hunting traditions, used not as a weapon directed at the animal itself, but as an environmental tool for shaping animal movement, encouraging a targeted individual or small group away from open grassland and toward terrain. Features more favorable to a prepared, waiting hunting party. This kind of landscape-scale coordination required exactly the sort of sophisticated planning, communication, and shared long-term memory of local terrain that anthropologists increasingly point to as a defining and perhaps decisive advantage. Separating human hunters from every other predator these enormous animals had evolved alongside across the preceding several million years. The archaeological evidence for coordinated, landscape-scale hunting strategy deserves closer examination in its own right, because several specific North American sites preserve physical patterns that go considerably beyond a single weapon fragment, offering a fuller picture of what a successful engagement with megafauna actually involved on the ground. The Lena and Murray Springs sites in southeastern Arizona, both extensively excavated across multiple field seasons, beginning in the 1950s and continuing intermittently since, preserve the remains of multiple mammoths recovered in close physical association with Clovis points and other stone tools, arranged in patterns consistent with animals having been processed at what researchers interpret as a natural water source or seasonal wetland, precisely the kind of terrain feature ethnographic evidence suggests would have restricted a large animal's mobility and made it considerably more vulnerable to a coordinated, prepared group than an encounter on open, firm grassland would have allowed. The presence of multiple individual mammoths at these single locations, rather than a single isolated animal, suggests these were not one-time chance encounters, but locations returned to repeatedly, precisely the kind of accumulated local landscape knowledge that would only be possible for a species capable of retaining and communicating detailed information about specific places across multiple hunting seasons and, quite possibly, across multiple generations. The La Brea tar pits in modern Los Angeles, while not directly a human engagement site in the same sense as Lena or Murray Springs, offer an illuminating natural comparison that helps illustrate just how dangerous unassisted encounters with Ice Age megafauna genuinely were. The tar pits preserve the remains of thousands of Ice Age animals, including numerous large predators such as dire wolves and saber-toothed cats, that became trapped while apparently attempting to scavenge or prey upon animals already caught in the sticky asphalt seeps. The sheer density of predator remains recovered from these deposits, vastly disproportionate to what their actual population density on the surrounding landscape would have been, demonstrates that even apex predators native to this ecosystem, animals possessing natural claws, teeth, and speed that Homo sapiens entirely lacked, regularly misjudged and fell victim to the dangers this landscape presented. Set against that backdrop, the specific, carefully engineered nature of the braced pike system, Byram and Sunseri identified looks considerably less like an optional refinement and considerably more like an absolute prerequisite for a species with no natural weaponry whatsoever to engage this environment with any reasonable prospect of consistent success. Zooarchaeological analysis of bone assemblages at multiple Clovis-era sites also reveals consistent patterns of systematic, skilled processing following an animal's acquisition. Specific, repeated cut mark patterns on particular bones associated with hide removal, meat processing, and marrow extraction. Patterns similar enough across geographically distant sites to suggest a shared, transmitted body of technical knowledge about how to most efficiently process an animal of this size, rather than each group independently improvising the process from first principles. This processing knowledge represents its own distinct technical achievement, separate from but complementary to the engagement technology itself. Successfully engaging a multi-ton animal accomplishes little without an equally sophisticated, shared understanding of how to subsequently convert that animal into usable food, hide, bone tools, and other resources before spoilage or scavenging competitors claimed the resource first. Understanding exactly which individual animals a coordinated human group would have realistically targeted within a mammoth herd requires understanding something about mammoth social behavior itself, reconstructed through comparison with modern elephants, their closest living relatives, combined with direct paleontological evidence from mammoth herd assemblages preserved at multiple sites. Like modern African and Asian elephants, mammoths almost certainly lived in matriarchal family groups, led by an experienced older female whose accumulated knowledge of seasonal water sources, safe migration routes, and local dangers would have been essential to the group's survival across a demanding Ice Age landscape. Adult males, based on the modern elephant comparison researchers consider the most reliable available behavioral model, likely lived more solitary or loosely associated lives outside the core matriarchal family unit for much of the year, potentially making them more frequently encountered alone, away from the protective structure of a larger group than females and juveniles typically would have been. This social structure carries direct tactical implications for how a coordinated human group would most plausibly have approached the underlying engagement problem. A full, healthy adult female mammoth, embedded within an alert family group led by an experienced matriarch, would have represented an exceptionally difficult and dangerous target. Not only because of her own individual size and strength, but because herd elephants, and by strong inference herd mammoths, are documented to actively defend threatened group members, with other adults capable of interposing themselves between a perceived threat and a vulnerable calf or injured companion. Ethnographic and behavioral evidence from modern elephant populations facing human pressure demonstrates that herds are capable of rapidly developing coordinated defensive responses once a threat is recognized. Precisely the kind of complication a prepared human hunting party would have every incentive to avoid triggering. Paleontological evidence from mammoth bone assemblages at several North American sites shows a demographic pattern consistent with human hunters, preferentially engaging young, aging, or otherwise vulnerable individual animals rather than prime-age adults in full health. A pattern that would make considerable strategic sense given the social dynamics just described. Juvenile mammoths, not yet grown to full adult size and not yet possessing an adult's full defensive capability, would have represented a considerably more tractable target than a mature adult. Provided a hunting party could successfully separate a juvenile from the protective structure of its surrounding family group. A tactical challenge in its own right, requiring exactly the kind of coordinated, multi-person strategy and landscape manipulation already discussed. Aging animals, particularly individuals whose worn molars, mammoths like modern elephants, relied on a sequence of 6 successive tooth sets across a lifetime, with the final set typically wearing down significantly in old age, had begun to compromise their ability to process sufficient food, would have been in a naturally weakened state, independent of any direct human intervention, representing another plausible category of preferential target, requiring less risk to successfully engage than a prime, fully healthy adult would have presented. This targeting pattern also carries a longer-term demographic consequence worth noting explicitly, because it helps connect the specific hunting mechanics this film has focused on back to the broader population-level extinction question addressed earlier. A hunting strategy that preferentially removes juvenile animals before they reach reproductive age, even while leaving most prime-age breeding adults comparatively undisturbed, can still exert severe long-term pressure on a population's overall growth trajectory, because it directly suppresses the rate at which each generation is able to replace itself. Modern conservation biology, studying the population dynamics of long-lived, slow-reproducing large mammals, including modern elephants, has repeatedly demonstrated that these species are particularly vulnerable to exactly this kind of pressure, since their naturally slow reproductive rate, a single calf every 4 to 6 years for modern elephants, with a comparable or possibly even longer interval considered likely for mammoths given their broadly similar body size and life history, leaves very little demographic buffer against any sustained increase in mortality among young, not yet reproductive individuals. A hunting pressure level that might seem, on its face, too modest to plausibly explain a genuine population collapse, could, once its specific demographic targeting pattern is properly accounted for, prove considerably more consequential over the span of many centuries than a simple head count of total animals engaged per year would suggest. This distinction matters enormously for understanding why megafauna across the world, having successfully weathered every previous glacial cycle throughout the preceding several 100,000 years, without any comparable population collapse, began disappearing in region after region, specifically coinciding with the documented arrival of anatomically modern humans in each area. It was not raw physical strength that gave human hunters their advantage. On that axis, a mammoth held every conceivable advantage over any individual person. It was coordinated planning, engineered technology, and landscape-scale strategic thinking, applied consistently, generation after generation, across a species uniquely capable of accumulating and transmitting this kind of specialized cultural knowledge forward through time. This brings us to the broader question this entire film has been building toward. Could human hunting technology and strategy, however sophisticated, genuinely have been sufficient on its own to drive entire genera of megafauna into extinction across multiple continents? This is the central claim of what researchers call the overkill hypothesis, first formally proposed by geoscientist Paul Martin in the 1960s. And it remains, more than half a century later, one of the most actively contested questions in the entire field of quaternary paleontology. Everything discussed so far has concerned North America specifically, but the broader pattern this film is investigating unfolded with meaningful regional variation. On every continent humans reached during the terminal Pleistocene and early Holocene. And briefly surveying that wider global pattern helps place the North American story in proper context. Australia presents perhaps the most striking comparative case, both because human arrival on the continent, currently estimated at roughly 65,000 years ago, occurred dramatically earlier than the peopling of the Americas. And because the megafauna involved were almost entirely marsupial, representing an evolutionary lineage that had developed in near total isolation from the placental mammal predators, including humans, present on every other inhabited continent. Diprotodon, the largest marsupial ever documented, resembled an enormous wombat the size of a small car and weighed as much as 2.5 tons. Procoptodon, a short-faced kangaroo standing over 2 meters tall, possessed a single large claw on each forelimb and forward-facing eyes unusual among kangaroo species, likely adaptations suited to a browsing rather than grazing lifestyle. Megalania, a monitor lizard potentially exceeding 5 meters in length, represented an apex reptilian predator with few parallels anywhere else in the world during this period. The extinction chronology across Australian megafauna remains less precisely dated than the North American record, complicating direct comparison, but the broad pattern, near total loss of the continent's largest animals within a window overlapping human arrival, occurring well before the most severe climate transitions associated with the end of the last glacial period, has led many researchers to view the Australian case as offering somewhat stronger support for a primarily human-driven explanation than the more climatically entangled North American record allows. South America presents a third distinct pattern. notable for the sheer diversity of megafauna present and for the comparatively late arrival of humans, entering the continent only after having already traversed North America and the narrow Isthmus of Panama. Alongside the giant ground sloths already discussed, South America hosted glyptodonts, toxodonts, large hippopotamus-like herbivores with no close modern relatives, and Smilodon populator, the largest known saber-toothed cat species, larger even than its North American relatives. The archaeological site of Taima in Venezuela, along with numerous sites across the Pampas region of Argentina, preserve direct evidence of human engagement with multiple megafauna taxa within a comparatively narrow window between roughly 13,000 and 11,600 years before present. A timeline that, once again, overlaps closely with the broader wave of continental extinctions. New Zealand offers a final, chronologically distinct data point worth noting, precisely because it demonstrates that this pattern was not confined exclusively to the Pleistocene. Human arrival in New Zealand occurred remarkably recently, only around 800 years ago, and within roughly a century of that arrival, all 9 species of moai, large flightless birds, the largest reaching heights of over 3 meters, had disappeared entirely alongside the enormous Haast's eagle that had evolved specifically to prey upon them. Because this extinction occurred so recently, well within the range of reliable archaeological dating and even oral historical tradition, and because it occurred with no plausible accompanying climate signal whatsoever, the New Zealand MOR extinction is widely regarded among researchers as one of the clearest, least contested examples of human hunting pressure, alone driving a complete megafauna collapse within a genuinely brief window of time. A smaller scale, more recent, and more definitively documented echo of the same broader pattern this film has traced across the far more ancient and more heavily debated North American record. The strongest recent quantitative support for the overkill hypothesis comes from an unusually well-controlled natural test case, the island of Cyprus of Hull. Published in early 2024, a research team developed a detailed stochastic population model examining whether the documented human population present on Cyprus during the terminal Pleistocene could plausibly account for the extinction of the island's only 2 megafauna species, the dwarf hippopotamus and the dwarf elephant. Cyprus offers researchers an unusually clean test case, specifically because of its late human settlement, its relatively small total land area of roughly 11,000 square kilometers, and its very low overall megafauna diversity of only 2 species, dramatically simplifying a problem that, on a continental scale, involves dozens of interacting species and confounding regional variables simultaneously. Feeding realistic estimates of human population size ranging between roughly 3,000 and 7,000 individuals, together with plausible human caloric energy requirements and modeled hunting efficiency rates into their population dynamics simulation. The research team found that human hunting pressure alone, entirely independent of any climate-driven mechanism, could readily have driven both endemic species to extinction within less than 1,000 years of initial human arrival on the island. Even more strikingly, the model's predicted extinction sequence, the dwarf hippopotamus disappearing first, followed sometime later by the dwarf elephant, closely matched the actual chronological sequence independently reconstructed from the island's genuine paleontological record. Once researchers had properly corrected for the well-documented statistical bias toward underestimating a species' true final extinction date based on incomplete fossil preservation. This represents some of the most direct, quantitatively rigorous support currently available for the core mechanical plausibility of the overkill hypothesis. Clear evidence that human hunting pressure alone, without invoking any assistance from climate change, disease, or habitat disruption, was mathematically sufficient to eliminate an entire endemic megafauna population within a genuinely short window of time under realistic, empirically grounded assumptions about human population size and hunting behavior. At the same time, an intellectually honest account of this debate requires acknowledging that the broader continental picture, particularly across North America, remains considerably more contested than the comparatively clean Cyprus case might suggest. A widely discussed 2021 study published in Nature Communications found that, across the North American continent as a whole, the specific timing of megafauna population decline correlated more closely with independently reconstructed climate change patterns than with reconstructed patterns of growing human population density. A finding that directly complicates any simple, universal version of the overkill hypothesis applied uniformly across every region and every species without qualification. Later research responding directly to this study has pushed back on specific aspects of its methodology and its underlying assumptions, and the resulting scholarly exchange remains active and unresolved as of this film's production. The 2021 Nature Communications study that identified a stronger statistical correlation between climate patterns and megafauna decline than between human population growth and megafauna decline deserves closer examination, because the specific methodology behind that finding illustrates exactly how genuinely difficult it is to disentangle these two variables using the available evidence. The research team behind that study employed a technique called radiocarbon-dated event count modeling, a Bayesian statistical approach that uses the frequency of radiocarbon-dated archaeological and paleontological samples across time as a proxy for reconstructing relative population size. The underlying logic being that a larger population, whether human or animal, should statistically produce more datable material entering the archaeological and paleontological record during any given period, allowing researchers to reconstruct population trend curves for both humans and megafauna independently, and then test which curve better predicts the timing of eventual megafauna decline. Applying this method across the North American continent, the research team found that reconstructed climate proxies, particularly temperature and precipitation patterns associated with the dramatic climatic instability of the terminal Pleistocene, tracked more closely with megafauna population decline than reconstructed human population growth did. This period of climatic instability is worth understanding in its own right, because it was genuinely extreme by any measure. The Younger Dryas, an abrupt return to near glacial conditions beginning around 12,900 years ago and lasting roughly 12 centuries, interrupted what had otherwise been a period of steady post-glacial warming, plunging much of the northern hemisphere back into severe cold within a time frame. Some ice core evidence suggests may have occurred over as little as a decade. Whatever its ultimate trigger, proposed mechanisms range from meltwater disruption of Atlantic Ocean circulation patterns to, more speculatively and considerably more contested, a possible extraterrestrial impact event. The Younger Dryas represents precisely the kind of severe, rapid environmental disruption capable of placing enormous independent stress on large-bodied animals already possibly under pressure from a separate, simultaneous human hunting presence. Critics of the 2021 study's conclusions, including subsequent work by Grayson and colleagues published shortly afterward, have raised methodological concerns about the specific dating datasets used and about whether radiocarbon sample frequency genuinely tracks population size as reliably as the underlying model assumes, particularly given well-documented biases in which types of sites and specimens tend to be preserved, excavated, and successfully dated in the first place. This ongoing methodological exchange is not a minor academic footnote. It reflects a genuine, unresolved difficulty at the heart of this entire scientific question. Both climate change and human hunting pressure were unquestionably present across North America during the relevant window. Both are independently capable, based on separate lines of evidence, of exerting serious pressure on large-bodied animal populations. Cleanly separating their individual contributions using data that is, by the nature of a 10,000-year-old record, inherently incomplete and imprecisely dated, remains one of the genuinely hard, unresolved problems in this field. And researchers on different sides of this specific debate continue to reach different conclusions using overlapping but not identical portions of the same underlying evidence base. The most current scientific consensus, reflected in a comprehensive 2024 review published in Cambridge University Press's Cambridge Prisms journal, increasingly favors a considerably more nuanced picture than either a pure climate explanation or a pure overkill explanation applied in isolation. Different megafauna species, across different continents and different regions, very likely succumbed to different combinations of these interacting pressures, with the relative weight of human hunting versus climate-driven habitat disruption varying meaningfully by species, by geographic region, and by the specific ecological vulnerabilities each individual species happened to carry. Recent work published in 2025 in the journal Global Ecology and Biogeography has further proposed that a critical, historically underappreciated variable in this equation may not be how naive any given prey population was to human hunters, but rather how experienced the specific human population doing the hunting already was, based on that population's own particular history and prior encounters with comparable large animals elsewhere, before ever arriving in a new region. The 2025 proposal that human hunting experience, rather than prey naivety, may represent the more decisive variable in this broader global pattern, deserves more detailed treatment because it offers a genuinely useful reframing of a debate that has, for decades, focused almost entirely on the prey animals side of the equation. The traditional naive prey framework, embedded in the overkill hypothesis since Paul Martin's original formulation, holds that megafauna populations encountering humans for the first time had no evolved behavioral wariness toward this particular predator. Since humans represented an entirely novel threat, their evolutionary history had never prepared them to recognize or respond to defensively. This framework predicts that megafauna extinction severity should correlate primarily with how recently and how suddenly a given regional population first encountered humans. With populations experiencing a rapid, sudden human arrival, the so-called blitzkrieg scenario, facing the most severe and rapid population collapse, since there would be no opportunity for behavioral adaptation to develop before the population had already been substantially reduced. The 2025 research published in Global Ecology and Biogeography proposes a complementary but distinct variable operating alongside prey naivety: the specific hunting experience and cultural technology already possessed by a given human population before it ever arrived in a new region. Human populations that had already spent many generations developing and refining megafauna-specific hunting technology and strategy in one region, the argument runs, would arrive in a newly encountered region considerably more capable of exploiting that region's naive megafauna population than a human population without comparable prior experience, even if the underlying prey animals themselves were equally naive in both cases. This helps explain a pattern that a purely prey-focused naivety framework struggles to account for on its own. Documented cases where megafauna populations in the tropical regions where humans themselves first evolved, where, by definition, prey animals had the longest possible evolutionary history of exposure to human predation pressure, and should theoretically be least naive, nonetheless experienced meaningful, if generally less severe and more gradual population pressure and localized extinction of particularly vulnerable species over time. As human hunting technology and strategy continued to improve, even in regions where the basic predator-prey relationship was already ancient and well established. This reframing helps explain why the specific severity and pace of megafauna decline varies so considerably from region to region, even among populations facing broadly comparable initial naivety. A newly arrived human population equipped with generations of accumulated, transmitted hunting technology and strategy, precisely the kind of engineered, tested weapon systems and cooperative landscape strategies this film has traced through the Clovis and Mannis evidence would be expected to exploit a naive megafauna population considerably more rapidly and more completely than a comparably naive but less experienced human population would. The specific technology available to a given human population, refined and accumulated across however many generations of prior hunting experience that population's ancestors had already accrued before reaching a new region, may ultimately matter as much for extinction outcomes as how defensively unprepared the prey population itself happened to be. Consider, too, what this entire body of evidence implies about the specific window of vulnerability facing any large, slow reproducing species anywhere on the planet when a technologically capable human population first arrives nearby. The pattern this film has traced, sophisticated, purpose-engineered weapon technology, coordinated landscape-based strategy, and a demographic targeting approach capable of suppressing population growth even without engaging every individual animal, recurs, in broad outline if not in every specific mechanical detail, across every continent humans have ever colonized, separated by tens of thousands of years, and by every kind of prey animal from a Cyprus dwarf hippopotamus to a New Zealand moa. The specific weapon changes. The specific animal changes. The underlying strategic logic, substituting engineered technology and cooperative planning for raw physical capability, remains strikingly consistent. This same demographic logic helps explain a pattern visible across nearly every documented megafauna decline discussed throughout this film. Extinction rarely required every single individual of a species to be directly engaged by human hunters. It required only a sustained, generations-long imbalance between mortality and reproduction, tipped just far enough by hunting pressure, layered atop whatever climate stress a given region was simultaneously experiencing, that a population already living close to its own biological limits could no longer replace itself quickly enough to persist. What emerges from this accumulated body of evidence, taken as a whole, is neither a simple, single-cause story of human hunters single-handedly eliminating the Ice Age's largest animals through weapon technology alone, nor a simple story of climate change acting in complete isolation from any human influence whatsoever. It is a considerably more intricate picture in which sophisticated, engineered hunting technology, precisely the kind of technology the 2024 Berkeley findings have helped researchers finally understand in genuine mechanical detail, provided human populations with a capability that, once present in a given region, interacted with existing climate pressures, habitat shifts, and each individual species' own particular ecological vulnerabilities to produce outcomes that varied considerably from place to place and species to species, even as the broader pattern across the planet, region after region, points toward human arrival as a consistently significant contributing factor. It is worth pausing too on what modern experimental archaeology of exactly this kind reveals about the broader scientific process this film has been documenting. The Berkeley team's testing rig, the digital reconstruction applied to the decades-old Manus specimens, and the stochastic population modeling applied to Cyprus's fossil record all represent genuinely different methodological approaches, developed by entirely separate research groups working independently, converging on a broadly compatible picture from three distinct directions. This kind of convergent methodological support, arriving from biomechanical testing, computed imaging, and population dynamics modeling simultaneously, carries considerably more evidentiary weight than any single approach could provide on its own, precisely because each method carries its own distinct set of assumptions and potential sources of error, and a conclusion that survives scrutiny across all three independent approaches is correspondingly less likely to be an artifact of any single method's particular limitations. None of this resolves every open question in this field, and an honest account of where the science currently stands requires acknowledging that, clearly. The precise relative contribution of hunting technology versus climate disruption continues to vary by region and by species in ways researchers have not yet fully mapped. The specific behavioral and demographic assumptions built into models like the Cypress simulation remain open to refinement as new evidence accumulates. And the Berkeley team's own planned follow-up testing, using more anatomically realistic targets, may yet reveal additional nuance in exactly how the braced pike system performed under conditions closer to a genuine encounter than a static wooden plank can fully replicate. What has changed decisively over the past several years is the confidence with which any single, simple story, either pure human overkill or pure climate catastrophe, told in isolation from the other, can be treated as a complete explanation. What this accumulated evidence ultimately points toward is not a story about any single hunt or any single animal, but about a fundamentally different kind of predator entering an ecosystem that had never encountered one before. There is a broader pattern worth drawing out from everything this film has covered, one that extends well beyond the specific mechanics of a single stone point and touches on something close to the central distinguishing feature of our species as a predator. Every other large predator that has ever existed on this planet has been constrained fundamentally by its own body. A lion's hunting capability is bounded by its own claws, teeth, speed, and strength, refined across millions of years of natural selection, acting directly on the animal's physical form. A short-faced bear, a saber-toothed cat, a dire wolf. Every one of these formidable Ice Age predators carried a fixed, biologically inherited toolkit, incapable of meaningful improvement within an individual lifetime, and only capable of gradual change across many thousands of generations of genetic selection. Humans arrived in this landscape carrying no comparable biological toolkit whatsoever, and compensated for that absence with something no other predator in the history of this planet had ever possessed at comparable scale. The capacity to externalize hunting capability into designed, tested, and iteratively improved physical objects, and to transmit the accumulated knowledge behind those objects forward through language and cultural teaching, rather than through the comparatively glacial pace of genetic inheritance. This distinction is precisely what the 2024 Berkeley findings illuminate with such clarity. The braced pike system is not simply a sharper stick. It represents a genuine engineering solution, arrived at through careful observation of a specific physical problem. How does a small, slow, physically unremarkable animal safely engage a much larger, faster, more powerful one? And refined through a design process incorporating fluted hafting for controlled shaft expansion, specific adhesive and binding technology, and comparative behavioral knowledge of how a targeted animal was likely to respond under specific circumstances. Every component of this system reflects cumulative, transmissible knowledge, built up and refined across generations of hunters passing specific technical insight to their successors, in a manner no individual human, however naturally gifted, could plausibly have reinvented alone within a single lifetime. This is, in a sense, the deepest continuity between the Clovis-era hunters this film has focused on and the modern researchers who spent years carefully testing and retesting their equipment to understand it. Both groups were doing fundamentally the same thing, observing a difficult physical problem closely, building and testing physical models to understand exactly how a specific mechanism actually behaves under real conditions, and refining their understanding incrementally based on what those tests revealed, rather than accepting an inherited assumption without direct examination. The population that first engineered the braced Clovis system 13,000 years ago, and the research team that finally reconstructed how that system actually worked in 2024, were separated by an almost incomprehensible span of time, yet were engaged in a strikingly similar cognitive process: patient, iterative, evidence-driven problem-solving applied to the exact same physical object. What ultimately made the difference between the megafauna of the Ice Age and the human populations that arrived among them was never a matter of individual strength, speed, or natural weaponry. It was a difference in kind rather than degree, an entirely different strategy for engaging the physical world, one substituting inherited biological capability with designed, tested, and culturally transmitted technical knowledge, refined generation after generation, until even the most physically formidable animals this planet has ever produced found themselves facing a predator whose true weapon was never the stone point itself, but the accumulated understanding of physics, animal behavior, and cooperative strategy that stone point represented.